take a look at these four series of numbers and tell me what is the relationship between the series and between each of the numbers in each series. It's kind of a rhetorical question. It's really difficult to look at data in this way and get any useful information. You have to look at it for a while before you start to see patterns in numerical data presented this way, even though there aren't an overwhelming number of numbers in it. However, if we plot these numbers on a simple scatter diagram, the patterns emerge. They emerge very, very quickly. You can see that there's a correlation between X and Y in each one of the series. You can see that it's stronger in some of the series than it is in others. You can see things like there's this third one here, there's an outlier. It doesn't seem to fit the pattern. Maybe that's just bad data. We should throw it out. Maybe we should adjust our model to account for this extraneous data point. The point is that we can see a lot more information a lot more quickly, often by looking at pictures of data than by looking at just the raw data itself. Pictures can be very powerful. I've been writing software for a really long time, and a part of my job over the years has been to present data to users in some meaningful way. And for years, I would use whatever tools were at hand. This is not a tools talk. I'll tell you there's a lot of great tools out there. Power BI is a good one. Excel is a great tool for visualizing data. And one of the reasons they're so great is because they're simple. You point the tool at your data set, and you pick the type of chart or graph that you want, and you click next, finish, and then bang, you've got your pie chart. But what if that pie chart is not the best way to display your data? Or a more fundamental question, what do I even mean when I say the best way to display your data? And this is something that I didn't think about for years. I hit next, finish. There's my visualization. On to the next problem. Most software people, I think, don't think about that. It's a solved problem. And the purpose of this talk is not to teach you how to use tools, but to teach you to stop and think about what are good ways to present data. Give you a few speed bumps. Before you hit next, finish, just step back and say, hey, you know what, can I improve this? Can I improve that? Because for years I wasn't really thinking about that. But until I read Edward Tufte. Edward Tufte is somebody who has been thinking about it for a long time. He's a retired professor at Yale University, and he's written extensively on the topic of data visualization. And a lot of the things I'm going to present today are based on his writings. When he first started studying this, many years ago, he started looking at pictures of data that spoke to him and trying to figure out why they spoke to him. For example, this is a train schedule in France. And you can see along the y-axis are the train stations. There's Paris, Montreux, Lourdes, Tonnerre, and so on. And along the x-axis are the times of the day. It's 24 hours. So these diagonal lines represent the routes that trains take to get from this station to that station. For example, this one right here leaves right around midi is noon in French. A little bit after noon, it leaves Paris, and it arrives in Tonnerre at a little bit after 6 in the evening, something like that. It's pretty simple once you understand it. It's not perfect, but it's pretty easy to read. Maybe the folks that are designing airline schedules could learn something from this visualization. So the simplicity is something that I really like and that Tufte really liked. Here's another one. This is actually 3 different streams of data projected onto a single x-axis. In this case, the x-axis is time. And the 3 pieces of data are, the red line at the bottom is the wages paid to a good mechanic in London during each decade. Basically the cost of labor. You can see it kind of gradually went up over the 300 or 400 years this chart shows. And then the bar chart in the center is the cost of a bushel of wheat. And it's so essentially the cost of commodities at that time. And that is also trending upward, but it's a whole lot more volatile than the cost of labor. And maybe a reason for that is at the top, these lines, these kind of curved lines along the top, those show the reigns of the monarchs in Britain during those periods. So maybe whoever was reigning during those periods had an influence not on the cost of labor, but on the cost of commodities, or maybe the wars that they were waging had an impact on that. I don't really know the answer, but this graph, because it's plotting three things along the same axis, allows us to ask those questions. It brings out those questions in the data. It brings it out very quickly. This is geographic data. This is from the United States, of course, and it's from the census, all census data. This is a lot of data. The United States is divided up into counties, and there's, I think, about 2,000 counties in the entire country. Each one of them is shaded here. The bottom shade shows the percentage of high-income families. This is from the 1960 census, I think, something like that. The idea is that darker shades represent the bottom half is the green is the high-income families. The red is the low-income families. So dark means there's a lot of them. So dark green means these counties in Southern California have a high percentage or had a high percentage of high-income families. In the southeastern United States, you can see there were a lot of low-income families, a lot of counties with a very high percentage of low-income families. So you can look at this, even though there are thousands of pieces of data here representing millions of people, we can very quickly glance at this from the shading is really, really nice that I can see where the rich folks were. They were, they tended to be in Southern California, up around the northeast part of the U.S. Southeastern United States tend to be doing very poorly at that time. Our brain could pick that out much better than if we'd used colors to represent that. If we'd said, okay, low income is orange and low percentage is orange, but high percentage is green, that wouldn't have worked very well. Shades work really well. Even if you're colorblind, shades work really well here. I noticed one thing that I've noticed here. I've never found an answer to this, but it looked like there are counties in Alaska. Alaska's way off to the side, but it's shown right here, that had both a high percentage of high-income families and a high percentage of low-income families. I've always wondered why, why was there no middle class in those particular counties, but really interesting. And in fact, where I live, is there a light on this thing? Let me see. I don't know if I can, I guess I can't projector light. I was hoping I can. But I live up in this, I grew up in Michigan. It's the one that's sort of shaped like a hand right here, and I grew up right about here. Southeast Michigan, it was doing very well in 1960. It's not doing as well now, but it's tied to the automobile industry. It's a very volatile economy because it has a single industry place. That map would probably look very different today than it did in 1960 when this census was taken. And that brings us to this graph that Edward Tufte discovered. It was created by a French engineer named Charles Menard. Edward Tufte referred to this as the greatest visualization ever created. The text was added later, so there's not a whole lot of ink to this. But this shows the advance on and retreat from Moscow by Emperor Napoleon, the general later Emperor Napoleon, during the Napoleonic Wars. And I'll just take 60 seconds to describe this graph. The lines, the tan line at the top is the route that Napoleon and his men took when they left Poland, entered Russia, and then advanced toward Moscow on the far right side. And the black line below is their retreat as they went back into Poland and returned to the rest of Europe. The width of those lines is proportional to the number of troops that he had at each point. So, knowing just that, you can really quickly glance at this and see what a disaster this campaign was for Napoleon. You can see that this tan line at the top gets narrower and narrower. Napoleon entered Russia with almost 500,000 men, and by the time he got to Moscow, he was down to 100,000 men. On the way back, it was even worse. That 100,000 men had dwindled to 10,000 by the time he limped back into Europe. Does anybody know why? Anybody have any history fans here? Right over here. What's a? I think it was a very severe winter when he was going in. Good. So the winter was a huge factor right here. So that's very true. So what happened was the Russians. What Napoleon was hoping to do was he had just conquered the rest of Europe by overwhelming his enemies with superior numbers, driving them out, and then living off the land. It worked until he got to Russia, but the Russians fought in a different way. Instead of fighting him directly, they retreated, and as they retreated, they destroyed their farms. They left scorched earth in their path, stretching his supply lines dangerously thin. And so Napoleon ended up losing far more men to disease, starvation, frostbite, desertion that he ever did to Russian bullets. And you can see that very clearly. That line gets narrow and narrow going eastward. And on the way back, that's when the winter hit. When he left Moscow, he came into a deserted Moscow. There was nothing there for him. He couldn't feed his men, so they left. And then that's when the temperature plummeted. And you can see down at the bottom here, this line, the very bottom is the temperature during his retreat. And you can see the dates here. It started out at it was -9 degrees, -21 degrees. It doesn't say whether it's Fahrenheit or Celsius, but it doesn't matter. It was dangerously cold, and that's what destroyed his men on the way back. So the retreat, the winter was the huge factor. On the way there, the scorched earth policy of the Russians was a huge factor. So I think you can see why Edward Tufte loved with this visualization. There's a bit of a description at the top that was added later. You know it was added later because it's in English and not in French. But in a single visualization with just a little bit of ink, Charles Menard was able to show number of troops, position of troops, direction of movement, time, and temperature. All of this with just a little bit of ink. Really jumps out at you. And it took me less than 60 seconds to describe what the graph was, and you can see what's going on there. All right, so these are good things. This is these maps, most of them were hand-drawn, but they're all examples of graphical excellence that spoke to Edward Tufte. He started thinking about, what does bad visualization look like? And in his words, and I would agree with this, the worst thing you can do with visualizations is to lie. To present data in a dishonest way, which does happen sometimes. In America, we have a news organization called Fox News, and they published this. They actually, on television one time, it was take a screenshot, during the presidential election of 2011. And it shows the unemployment rate in the United States during the previous 12 months. It looks okay. It goes up and down and so on. I don't like the fact that it doesn't show zero, so it seems to be more volatile than it really is. But that's not the big problem with this. The big problem is that the November, right before the election, look at the numbers, 8.6% unemployment, which is an accurate number, but look where it's graphed. It's graphed at the same level as 9.0. 8.6% is actually the lowest number on this graph, and yet it's plotted as one of the highest points. And the fact that Fox News had actually endorsed incumbent President Obama's opponent leads me to believe that they were deliberately trying to mislead people with that by not showing that unemployment had gone down right before the election. So my guess is that this was probably a deliberate attempt to mislead their audience. It was a blatant lie, which happens. Not all. Here's another one that I think is deliberate here. This was from a mining company. I took this out of Tufte's book, but I don't think a mining company exists anymore. And this shows the net income during 5 years. It was taken out of an annual report for the mining company. And you can see this number right here is a negative number. It's not at all obvious that's a negative number because it's represented as a tall vertical line, which seems to suggest maybe it's a positive number. No, they lost money that year. And I think they were trying to hide the fact that they lost money by presenting it in this way. That's my guess. And the problem with doing so is that when you see that and you think to yourself, they're trying to mislead me, it causes me to call into question every number in that report, which is, I'm sure, the exact opposite effect they were hoping to have. So once you catch somebody in a lie, whether it's deliberate or not deliberate, you start to question their integrity, you start to question their veracity. Yeah, so they would have been helped if they just put a zero line there indicating what is, or maybe a different color to say this is negative, something like that. This is also why. This is from the New York Times, and this one I actually don't think is deliberate. I can't prove it, but my feeling is that it was done in order to deceive people. This shows well, they need a little more history here. I'm going to give a little history this hour. In the late 1970s, in the United States, we were all driving these gigantic cars with Corinthian leather, and they had very poor gas mileage. And then we had an energy crisis. A lot of our oil came from the Middle East. The Middle East started cutting off our supply of gasoline, of oil, which meant less gasoline or more expensive gasoline. And the United States government said, you know what, we need to start buying manufacturing and selling more fuel-efficient cars. They said to the auto companies, we're going to mandate that you sell more fuel-efficient cars. And what I mean by mandate is they said, okay, here's the target number. Add up all the mileage of all the cars you sell, divide it by the number of cars, and the miles per gallon had better be this number. And if it's not that number, there will be penalties. There will be financial penalties. It's a pretty serious thing. And tough on the cars company, especially since it takes a while to design a more fuel-efficient car and to manufacture it. So the good news for the car companies was they didn't implement it all at once. Over the years, they said, okay, year one, that number has to be 18 miles per gallon, and then about 10 years later, it goes up to 27.5 miles per gallon. That's what this graph is indicating here. Every year, it went up a little bit. The mandated miles per gallon that the car manufacturers had to manufacture and sell had to be that number that went up a little bit every year. And they're represented by this number. You can see the numbers on the right, 18, 19, 20, 22, 24, et cetera. Those are the years 1978, 79, 80, and so on. That number gets bigger, and the line that represents that number gets bigger every year. The really big problem with this is that, 27.5 is bigger than 18, and that line is bigger than the 27.5 line is bigger than the 18 line, but they're not proportional. I mean, the 27 is a kind of bigger. The line is way bigger. They're not proportional. So it's misleading. And one of the contributions of Edward Tufte is he created one of my favorite statistics in all of stats, which is what he calls the lie factor. We can look at this graph and we say, you know what? This does show the direction of change. Those lines do get bigger as time goes on. Maybe the magnitude is off by a bit. So what? As long as it's showing the fact that they're getting bigger, maybe that's enough. But how much is it off? Let's measure. That's what the lie factor does. It's the size of the effect shown in the graphic divided by the size of the effect of the data. And in this case, this number, 27, excuse me, from 27.5 to 18 increased by 53%. That is a significant increase for sure. But that line increased by almost 800%, 783%. So this thing, the magnitude is not off by a little bit. It's off by a lot. It's lying to us almost 15 times over. That's a lot. It's very misleading. And I said earlier that I don't think this was done as to mislead the reader. That was, I don't think the New York Times had an agenda that they wanted to present this data, incorrectly. Yet they did. And I have a theory why they did that. I wonder if anybody else wants to throw out an idea why they think, other than just wanting to mislead people. What's another reason why they might present data this way?
Artistic. It looked like a road.
That's my theory as well. He said artistic. And so the reason is that the person that created this graph was not a statistician, was not an engineer, was not an automotive reporter. The person that created this graph was from the art department. And the person that, the editor that commissioned this graph was more concerned with making it pretty than they were in making it accurate. That they wanted to make it accessible. They thought, it's kind of insulting, really. That our readers really won't be interested in this unless we kind of jazz it up and make it look, with this 3D perspective and make it look like a pretty thing. The nice-looking part of this graph was more important than making it truthful. And it's still a lie, whether it was deliberate or not. It misleads the viewer because you're going to look at that graph before you look at those numbers. Actually, I plotted these numbers here. That's what they are. It's actually, it did go up. It went up significantly, but not nearly at this, 15 times rate that's suggested by the earlier picture. All right, here's another one. This one shows the shrinking family. What this means is that it used to be, when I was a boy, there were a lot of general practitioners in the medical industry. The people, they're either family practitioners or general practitioner, a doctor, just kind of did everything. He took care of your whole body. That's less true now. Nowadays, doctors tend to specialize. There's just way more money in specialization. And that's what this graph is trying to show. In 1964, 27% of all doctors were generalists, and by 1990, only 12% were generalists. And that's what we're showing here. I don't like the fact that there's the x-axis isn't quite proportional. That's not the big problem I have with this. The big problem I have is they're trying to show the shrinking number from 27 to 12 by these shrinking pictures of doctors. And again, they're making it look pretty. It's a nice looking doctor there. But the real problem with this is that 12 is about half of 27 or so. And this doctor is about half as tall on the right as he is on the left, but he's also half as wide. And as you learned in, third grade, the size of an object, of a two-dimensional object, is proportional to both its height and its width. So this doctor on the right isn't half the size, he's about fourth the size. So the lie factor, just by the fact that it's going, we're using a two-dimensional object that varies in both the x and y, is going to lie to us. So the data changed. I'm going from right to left here. It's easier to do the math. The data changed by 125%. The graphical changed by 406%, just simply because we varied both the height and y. This isn't always true. Bar charts, for example, they have both height and width, but typically the width does not change. So those are more honest than this was. But again, I think whoever published this, I don't have the source of it, was trying to make it look pretty. They thought, oh, our audience, they won't really look at it unless we have some fancy picture of a doctor that varies. And this is, so a lie factor of 3.8%, just simply because of the changing x and y here. And I won't do the math here. Well, I guess I will do the math, but this problem is even worse when you use three-dimensional objects, because for three-dimensional objects, vary by both their height, their width, and their depth. So this thing that's showing us the price of a barrel of oil, also during the 1970s when prices were going way up, now we've got, this is proportional, the height is proportional, but we're also varying both the width and the depth here. So the data changed by about 554%. As far as I know, this is a record lie factor. All right. And this is, I actually found the same data in another book that shows those numbers here, where it's, this is the same data more or less as this right here, but presented more accurately. This also shows real versus nominal dollars, which is really important, especially in times of high inflation, which in the US we had that in the 1970s. Because real dollars are adjusted for inflation. A dollar spent in 1979 was worth a lot less than a dollar spent in 1972. So adjusting anytime you're using monetary values over a long period of time, you should always adjust them for inflation. Here's another one here. This is slightly misleading. This is, I don't know if people use travel agents anymore, but these are commissions paid by travel agents to 4 different airlines. In fact, I don't know if only one of these airlines even exists anymore. Oh, no, Delta exists. But this shows for 3 different periods. And for each of these 3 periods, so the commissions paid from period 1 to period 2, it went up, and from period 2 to period 3, it went down. That was true for all 4 of these airlines. What's not obvious until you look at the fine print is that third period. In the fine print down here, it says this is only the first half of a year. It's only a 6-month period. So of course it went down. It's not really helpful to even present that information. A better visualization would be either to annualize that number or to split the other 2 numbers into 6-month periods. So it's just misleading here. We're trying to compare a 12-month period to a 6-month period. For some of these, like for the TWA one, we can't even tell if it's proportional without doing the math ourselves, which defeats the whole purpose of the visualization. Context is really important. If we see just a part of the data visualized without seeing the whole thing, then that can be really misleading. Or here's one that doesn't have units. Happiness versus, buy our product, you'll be happier. We'll just plot that on a thing here. But what's our units for happiness? I know how many I own. It looks like I'll buy 10 of those, I'll be 10 times as happy. But how are we even measuring that? There's no context for that. Here's some real world example here. This is a data from the state of Connecticut in the US, the traffic deaths for 2 different years, 1955 and 1956. The reason I picked those 2 years is because that was the year that they implemented, they started enforcing speed limits on the highways in the state of Connecticut. And you can see, I also have one problem here is I don't show the 0. I've just at least got a little marker there to indicate the 0 isn't on there. But anyway, traffic deaths did decrease between 1955 and 1956 in Connecticut, and that's good. So that you might look at that and think, oh, well, you know, enforcing speed limits saves lives. Seems like a reasonable conclusion to draw, but you can't draw that from this data because you don't know what you don't know what happened before 1955, you don't know what happened after 1956. It could look like this or this or this. Maybe that was just a blip, maybe it was a permanent change, maybe it was just going up and down all along, it was that volatility. We're only looking at 2 pieces of data in here. We really need more context to see that. So I looked up the context here, and this is the data. There's the 2 points that we were looking at. There's the data from before 1955 and after 1956, and you can see it was trending upward. The number of deaths, traffic deaths, was trending upward in the state in the few years before that, and it went down and it stayed down. It continued to go down. So here's some really strong evidence providing context to say, yeah, driving slower or forcing people to drive slower does in fact save lives. It's intuitive to us, but still, this is data that backs it up. Here's some even more context. These are the states that are contiguous with Connecticut, and those took longer to enforce speed limits. And you can see Connecticut, the blue line, is the only one that's trending downward after 1956. The other ones either went up or stayed about the same. So this context adds a lot more veracity to the argument that driving slower saves lives. All right, let's see. So here's just, I've been talking for a few minutes. These are the takeaways from this section here. Keep your data representation, your visual representation, proportional to the data. One way to do that is just to recognize what the proportions are. The other way is just don't fall for this trick of varying both the height and the width, or the height, width, and depth. Keep the dimensions of your graph equivalent to the dimension of your data. One-dimensional points of data, one-dimensional graphic points. Adjust dollars for inflation, especially when you're doing over a period of time, and provide context in whatever you're presenting. I'll pause now if there are any questions at this point and to clear my throat. No questions. All right. Let's move on to something called Data Inc. This is actually, when I read Tufte, this was the most eye-opening part of what I read, because this is what changed the way I work the most. The Data Inc. ratio, Edward Tufte invented this ratio. It's simply the amount of ink divided by the amount of data ink divided by the total ink. Of course, most things we don't print anymore. Most of the things are just on screen, but there was a time when we would actually put things on paper and present them. And the dark parts were the ink. So we'll still think of that. The dark parts on your computer screen, that's the ink. Not all ink is data ink. So this ratio brings up the question, what is data ink versus what is not data ink? Well, I'll tell you here. There's some stuff, some of that ink, some of the dark parts on your visualization are redundant data. If you are representing the same information more than once, then only one of those representations is data. So you may have, if this will reduce your data ink ratio. The highest this can get is 1.0. If every single bit of data on, every single bit of ink in your visualization is data ink, then this will be 100%. It'll be 1.0. It'll never go above that. And your goal should be to increase this value as much as possible within reason. And I'll talk about that within reason in a bit. But anyway, so redundant data, if you have the same data represented multiple times, only one of those is data ink. That will reduce your data ink ratio. For example, here is a bar chart representing a single piece of data, the number 35.9. Let's count the number of ways it's represented. Here we have a vertical line here. It's 35.9 units tall. Another one over here is 35.9 units tall. We have a horizontal line, 35.9 units from the x-axis. The shaded area is 35.9 units tall, and we have the number 35.9 itself. There's a lot of redundant information just for just one piece of data here. So not all of that. This has a fairly low data ink ratio. Also, the number 35.9 is 35.9 units from the x-axis. And I won't do the math here, but this is, if we use, a lot of people fall in love with three-dimensional bar charts. They're not bad per se, but they do have a very low data ink ratio. There's even more wasted ink in here. All right, so redundant information is one thing. Metadata. Metadata is not data, it is information about the data. For example, in this chart right here, this is a simple scatter diagram. I just made this up. It doesn't really matter what the x and y values are. But the data in this are just those little dots, this scatter diagram. It isn't the grid lines. It isn't the numbers on the side. The data is just the dots, so that's the only data ink in here. But there's a lot of other ink, a lot of information about the data in here. And I can make this graph better by removing some of that metadata, like this. Before, after. So now those extra grid lines are gone, and the grid lines in between are lighter. They're light gray. If anybody remembers back when spreadsheets were first introduced, the very first versions had black lines in between the cells. And by the second or third version, they had light gray lines because the creators of tools like Lotus and Microsoft Excel discovered that lines, those borders of the cells, they're not data, they're metadata. They are just there to divide things. Let's move that out of the way and into the background. They help, but let's let the data is the number inside of the cell. Let's make that jump out more, just like this does. So when I remove this, see how the data just jumps out a lot more? It's a lot clearer. We can see that a lot more. In fact, do we even need those lines? Let's just get rid of those. The data jumps out even more. Do we need the borders along the top and right? I don't think they help. I think this is better. And I also removed some of the numbers in between and the x and y axis. Do I need that diagonal line? That's a trend line. I can remove that. In this case, I see the data a little bit more, but I think that trend line helps. I'm going to put it back. So this has a higher data ink ratio. This has a lower data ink ratio, but I like it better this way. I like that trend line helps. It shows that we're moving upward, and we're moving upward in a linear fashion. So that's why I say within reason. This is an iterative process. And this is what I started doing when I first read Edward Tufte. I started creating my visualizations, next, finish, and then I would step back and I'd say, what can I get rid of in here? And I would get rid of it, and then I would step back again. I would say, is it better? And if it's better, I would leave it off, and then I'd look for something else to get rid of. But sometimes, something like this, I might add back in. This had a profound change on the way that I did my work as a computer scientist. Here's another one. This is a real one from Linus Pauling. Linus Pauling is a hero of mine. He was the only man to win a Nobel Prize in both physics and peace, and I actually have a degree in biochemistry, so I studied him in university. And this is showing the atomic number versus the atomic volume of certain elements, which each dot represents an element. And Pauling got it. He got the fact that I don't need all these grid lines. Let's put pluses instead, just to indicate where the lines are. And I think it's much better this way than having a bunch of harsh, dark lines indicating those grids. But because I think I'm smarter than Linus Pauling, I decided to improve it here and get rid of those pluses as well, and get rid of some of the things along the x and y axis, and get rid of the borders on the top and right. And I think this is even better. And I could increase the data ink ratio further by getting rid of these lines that he's drawn between them. But now it just looks like a bunch of dots. I'm going to put those lines back. I think I'll put them back, and I will add some, the element of the first one. These lines represent the rows in the periodic table. So each row represents another shell of electrons. And so this is significant. In physics, this is a big deal. From sodium to potassium, Na to K, that another shell of electrons comes on here. So these groups are significant, and I see that by adding these trend lines. So even though this has a lower data ink ratio than that, I said higher data ink ratio is better, still it's an iterative process. This, I think, is the ideal way of presenting this data right here. All right, so think about the data inc ratio, maximize it, but maximize it within reason. Another example of how sometimes lowering the data inc ratio is from this graphic, which I showed on the very first slide. This is that train schedule. There is one flaw, well, there's actually multiple flaws in here. But one big flaw in this is what happens if a train is in transit at 6 a.m., because 6 a.m. is the far left and the far right. Then our eyes have to do this right here. It's kind of a mental speed bump. We got to look over here and then come find the same thing over here and continue it. That's a chore. And we can actually improve this graphic by reducing the data inc ratio, which I said don't do, but we can. This is better. Now we don't have to do that. We just take the first half of the graph and paste it again. Now we've got some redundant data. We've got some extra metadata. It worsens the data inc ratio, but it does make it more readable. So you're not just applying a formula to this. And of course, you probably figured out that we could probably increase the data inc ratio by getting rid of a lot of these grid lines. There's just too many grid lines here. So we can offset it in other ways as well. All right, so this section here, just some takeaways from it, and I'll provide a link to the slide deck if anybody wants it afterwards. And is that, number one, what is the data? What are you trying to show? And show that data. Number one priority is the data over everything else. And think about the data inc ratio. This was like an epiphany for me. The data inc ratio, I had so many projects as a consultant that said, replace this Excel system with client-server database system. But we wanted to look just like Excel, and with all these grid lines and everything like that. No, and I'd say, let's remove these grid lines, see if it looks a lot better. So maximize that data inc ratio, present it to your viewers, but within reason. It's not dogma. So you can do so by erasing non-data inc, getting rid of the redundant data inc, and it's an iterative process. Remove things, step back, decide if it's better or not. If it's not better, put it back. If it is better, then find something else. All right, questions on this? This is the big part of the presentation, I think. All right, next thing is vibrations. This is less of an issue now, but when we used to print things out on black and white laser printers, we do things like this. And vibrations are just the fact that when you stare at this, it kind of looks like it's moving. There's a thing called the moire effect. And staring at it can actually cause seizures in some people because they see vibrations in this that aren't really there. It's an optical illusion. But we used to have to do that a lot. We'd create things like this that are just unreadable. Or we'd have legends right here. I really dislike legends. If we can avoid them, then we should avoid legends right here, where we have to look up at the top and then look down at the bottom and figure what's what. I think I have a better example right here. Oh, here's one. This is I created this from some newspaper article data. This is from I think it's from 1972 in the U.S. And these are the number of articles printed about different topics in the U.S. And inflation, unemployment, shortages. The reason I think it's 1972 is Watergate was a big political scandal 50 years ago in the U.S. And so now to look at this, you have to look and say, oh my gosh, there's some diagonal lines that go from bottom left to top right, but there's multiple ones of those. We have so many that we have to figure out the spacing between the lines, and our eyes are looking back and forth from the legend to this bar. It's another mental speed bump. It takes a long time to absorb this stuff. And a better way to do that is to maybe get rid of those vibrations and those patterns. One, for people that are epileptic, for example, you don't have that problem with moire effect, which can cause seizures. And just label things directly. If you just label these directly, then this is much more clear. And I showed this one time to an audience, and somebody said, well, that's clearer, but I can't tell whether, let's see, which is higher, competence versus crime. Are those the same, or was one of them or race versus inflation? Why don't you sort them? I thought, oh, that's a really good idea. And so this came from an audience member. This suggested this, and now I can actually compare them. I said, wow, it looks like the confidence, articles about confidence in politicians there were a lot more of those than there were about unemployment. Unemployment apparently wasn't a big issue, at least not in the popular press. And so, way better. If you guys have things you want to add to my slide deck, I'm all ears. This gets better every time I give it. Here's another one here. This is, pie charts. I really generally dislike pie charts. The only advantage that a pie chart has is that it emphasizes the fact that the numbers add up to 100%. So if that's the biggest thing that you want to show is that they add 100%, then okay, use a pie chart. But other than that, they suffer from the same problem as one of the earlier graphs. It's really hard to tell, to compare which one is bigger here. This one also suffers from the fact there's just way too many data points in here. These wedges get lost in this extreme amount of data. Same thing with this one here, though hugely low data ink ratio. Whoever created this was really trying to make it look pretty and not trying to make you grasp the data very quickly, which is, I think, the biggest advantage of data visualization. All right, I want to talk about something called chart junk and ducks. These are synonyms here. Chart junk, this is stuff that isn't even metadata. It's just prettiness, just meant to jazz up your, your visualization. And the word ducks, Tufte coined this word. The reason he came up with it is there's a building in the northeastern United States. It's shaped like a duck. And the only reason it's shaped like a duck is so that people driving down the street will go, hey, look, there's a building shaped like a duck. Let's go check it out. Nothing about the duck shape makes it a better building in any way at all. So he called these things ducks. But I think chart junk is a really good word as well. You know, things like this. You know, why is this monster thing here? We're showing some information, I don't know, campaign expenditures year by year. Again, whoever created this graphic, they were all about trying to snazz it up and make it look pretty. And it doesn't add anything to the value. In fact, it slows down. I'm distracted by all this monster thing. I'm distracted by the lady's legs that were, what is this doing? Average price of a diamond over time. If you're doing this a lot, I mean, it might be a novelty the first couple times you do it, but people tire of these things after a while. Here's one. This one actually, the reason I think they were trying to emphasize the fact that there's a downward trend here, which is why those bar charts are trending downward. But now I don't even know, do I look at the left side of each bar, or do I look at the right side? That's not even clear to me. So it actually detracts from the accuracy of this graph. Only one of those is actually correct. So things like that. This is all just chart junk, extra extraneous information, lots of colors. Let me find a good one here. Oh, this one right here. This is trying to show colors. Values based on colors. And, you know, remember the map I showed before where light red meant low percentage, dark red meant high percentage? Our brain can pick that up instantly. Going from green to purple, no, we don't. Our brains just don't do that. This is practically unreadable. Oh, what do we have here? This is an old telephone, you know, back used to hang on the wall, and nothing about the shape of it. It's shaped like the country of Ireland. And it doesn't make it a better telephone by shaping it like Ireland. But the reason I put this in here is because my birthday is coming up, and I think this would look really cool on my wall. So if anybody wants to get me an Ireland-shaped telephone, I'd be totally okay with it. Don't tell Edward Tufte that I like this thing, but I think it's pretty cool. Violates everything I've been saying up to this point, though. And then there's this one here. This was from one of Tufte's books. It came out of, he pulled out of an education journal. And what it's showing is the percentage of students under 25 and over 12, or 25 and older, over a 5-year period. All right. And so this really just 5 data points. I mean, there's 10 data points, but 5 of them are just 100% minus the other one. So to show these 5 or 10 data points, the person that created this, they used 5 different colors, and they used this 3-dimensional thing. These curves probably mean nothing. They just curved it because to make it look a little fancy. And then here's one thing that's really weird is that I know that this number is 28, And that number up there is 72. That adds up to 100%. Every one of these adds to 29.2 and 70.8. These all add up to 100%. And even though I know this to be true, I look at this graphic and I don't see it. Just seeing the fact that they all add up to 100% is, even that simple thing isn't apparent in this graphic because they've dressed it up with all this chart junk and they just tried to be cute with everything. And so this is actually in his book, and I always wondered if maybe the person that created this and put it in an educational journal might be in the bookstore thumbing through and see their graphic and be all excited until they read what he wrote about it. But I started thinking about, is there a better way to present this data? And I came up with this. This is really simple data. You don't have to visualize it. Visualizations are most effective when you have a lot of data and you want to present it quickly. This one, I mean, you could add that other one. This is just subtract 100% from it. But simple data like this, you can visualize it, or this one, well, it just jumps out at it really quickly. So visualizations aren't necessary. They add more and more value when the numbers themselves get complicated or they get massive. All right, let's see. I only got about 15 minutes left here. I've got a couple things. This is really hard to do. I just want to show you this. There's some clever ideas that I've seen. If you wanted to reduce your data ink ratio, one way is to use the same ink to do multiple things. Like this, some clever desk sergeant during World War I typed up for each month the troops that were deployed from England to France, and these are actually the division numbers of the troops that were deployed. He used the numbers themselves as data points. Here's an interesting graphic where there's nothing that says that you have to have X and Y labeled with all your data X and Y. You can have, in this case, the X-axis values are in fact the data points. There's nothing that says that you have to have equidistant in between each data point. These all have really low data ink ratios. Software would be hard to do with some of these things, but I just thought they were interesting ideas. I'll talk a little bit about data density because, as I said, if you're doing good data visualization principles, it shouldn't matter that you're presenting lots and lots of data. Our brains, if we present it well, our brains can see data. So something like this is kind of a meaningless ratio now. The number of entries in a data matrix divided by the area of the data graphic, that's the definition of data density. But we don't really know the area because we're not printing things anymore. But it's something, this was in a magazine. It's obviously not very dense. It's very low data density. The first bar is just the sum of the other two. There's only a couple of data points here, lots of wasted space. Low data density. This is high data density. It's weather in New York City every day for an entire year. We've got the temperature of every day graphed in that jagged line in the middle. We've got the relative humidity along the bottom. We've got the average, precipitation versus the normal precipitation in these bars in the middle here. So we can say, it looks like March, there was a lot more rain and snow in March than there usually is, a lot less snow in January than there usually is, things like that. We can see that. It's all along the same axis. In this case, it's the months of the year and the days of the year. So we can compare these things really quickly. Lots of data. Don't be afraid. I guess my lesson here is don't be afraid to put a lot of data into your visualization. If you're doing it well, people's brains can pick that up. This is the sunlight every single day for every single hour of every single day for a year. The dark, I don't know why they use dark to represent sunlight. It should be white to represent sunlight. But the dashed line is just sunrise and sunset. So in the summertime, of course, the days are longer. And you can see that there were a lot of bright days in June. There were some overcast days in early April. We're seeing these patterns here really, really quickly. Our brains can pick them up. Don't be afraid to put thousands and thousands of pieces of data as long as it's presented well. It's good. Let's see. Small multiples. I'm going to go through this really fast. This is just another way of presenting extra dimensions to a data. If you want to show changes over time, you could also do this with animations. A lot of software now allows that. But before we had animations, this is a hand-drawn map or a graphic of the average age or the age of fish being caught in northern European streams. And you can see that the age is sort of shifting to the right every year, indicating that the fish are getting older, indicating that these streams are not being overfished. The fish are being allowed to age. This graphic here is the average age of Facebook friends. And they tend, your Facebook friends tend to be about the same age as you are, particularly when you're younger. You're 15 years old. Most of your friends are 15 years old. When you're in college, they're about the same age as you. As you get older, you acquire friends at different ages, and so this graph gets more and more spread out until when you get really old, your friends start to die off, and now everybody's younger than you. And so just showing this, essentially the same graphic with one variable change. You can do the same thing with an animation, but this is another way of presenting this. This one right here, I'm ready for time. Let's see. Oh, good. All right. I like this one here. It's got a lot of information in it. This is from a magazine that rated automobiles. And again, it's a lot of information, but with about 60 seconds of explanation, I can show you that each one of these rectangles represents a make and model of a vehicle. And along each one of these rows represents a potential problem of this vehicle, like the exhaust system or the fuel system or the ignition system, something that can go wrong. Along the top of each card, we have the make and model year, 1976, 77, 78, 79, 80, and 81. And then the real data here are these circles. A light circle indicates no problems at all. The 1978 Subaru had 0 problems with its suspension. A dark circle indicates lots of problems. So the 1976 Plymouth Volare had all kinds of transmission problems. It was just really a mess of a car. So just knowing that in the 30 or 60 seconds I showed you, you can just take a step back and say, oh, which cars were more reliable? It looks like this Plymouth Volare was a piece of crap for years. It looks like the Subaru was bad. It's got a lot of dark color on the left, but it got better as time went on. Boy, this Toyota Corolla, you want a maintenance-free car in the 1970s? That was a really good car. So anyway, lots of information presented with just small things varied, in this case, the make and model of the vehicle, and we can just step back and see it. It's presented really, really well. And I want to show you, the last thing I want to show you is some things that Edward Tufte invented. He invented 2 types of visualizations, one of which is used a lot, and one of which has kind of fallen by the wayside. So the one that's used a lot is called spark lines. And a spark line is a really high data inc ratio because it doesn't try to show all of the information. It just shows really key points with labeling the start, the end, and the highs and lows, and then just showing the volatility along the way. So you don't get all the information, but you can really quickly look. It's used a lot in financial papers. The Wall Street Journal will show stock prices over time. And you can really quickly see whether a stock is trending upward and how volatile it is by looking at this. And the key points would be where it starts and stops and the highs and lows. They might label those explicitly. If you go into Excel, you can actually put it in a graphic inside of a single cell that represents the entire row, and it'll create a spark line at the very end of that row that looks kind of like this. So we see this a lot. This really works well in financial. This is exchange rates over either 65 months, euros versus other currencies over different time periods. And you can just get an idea, how did the euro do against the dollar over this 5-year period? Looks like it started and ended at about the same spot, but it dipped in the middle, things like that. And then this slope graph here, this is just, I don't think people hasn't really caught on. I was only able to find one of these. It's just essentially just showing a couple of data points and how much they changed over time. In this case is amounts spent by each country between a 9-year period. Looks like Sweden in the 1970s, they increased their spending a lot, whereas Britain decreased their spending during that same period. Somebody sent me this one. I was in a talk and I said, I've never seen one in the wild, and somebody actually said, hey, here's one, and this is confidence in government and U.S. government institutions over a 9-year period. So it looks like confidence in churches went up. I guess not just government, but institutions in general. Confidence in churches went up during that period, but confidence in what went way down? Confidence in banks went way down, and confidence in Congress went way down during that period. So it's out there, but it's not really used that way. The spark lines are used a lot. All right, and finally, I've got 6 minutes left. Number 1, don't lie. Graphical integrity is important. I get that some people, your job, your boss tells you, make the data say this, But be aware, there's a cost to that. That when people see you misleading them with your visualizations, that all you have is your integrity. All you have is your credibility. And if you start to lose credibility, then it's going to defeat the whole purpose of what you're trying to do. And then the number one thing that I took away from this and how I worked and how I changed things is the data ink ratio. Think about that data ink ratio and maximize it within reason. Avoid redundant data, avoid these chart junks and ducks. They don't really add anything at all. Multifunctioning graphical elements, they're cool if you can do them. They're really clever. Do keep the labels of data. If you can avoid legends, absolutely. Label these things directly. And don't be afraid to maximize your data density. Other considerations. Let's see. Think about who your audience is. I had some things with color in here. You may have the colorblind people that are going to be looking at this. Think about what colors contrast more of those. Label things as much as you can. So there are other considerations as well. A good title to a graphic can add a lot to it. So you don't need a lot of text, but just labeling things really well helps a lot. All right, let's return to this one. This was the one from Charles Menard, a French engineer, Napoleon's march on and retreat from Moscow in the Napoleonic Wars. Menard, he could have presented this data in a different way. He could have done whatever the 19th century equivalent of next finish is. He could have used his artistic skills to kind of snazz it up, but he didn't. He chose to present the data in a simple way, using a little bit of ink. And that's what I want you to think about when you're doing your work, is I'm creating my visualizations. Start thinking, just take a step back. And don't, before you hit finish, how can I do this? How can I make this better? Can I remove some of the metadata? Can I get rid of some of the redundant data? Is there things that I can do to make the data itself jump out at my users and make it real clear? What is the data in here? What is the important part of this visualization? And maybe if I do that, maybe I can add other information on here along the same axis, which makes it more relevant and would raise questions and provide some context to this. This is what I want you to do. That's the whole point of this talk, is just to provide you a speed bump in your mind to erase the speed bumps in your viewer's mind. This is what changes data into information. This is what your users will thank you for. My name is David, and I thank you. There's a few more links in here. If anybody wants this slide deck, go ahead and scan that barcode or type in that thing. I have 2 minutes left. I will answer questions for 2 minutes, and then I'll step out in the hallway if anybody has other questions. So, way in the back there, sir.
Hi, thanks for that firstly. Given the more modern way people interact with data now compared to obviously the more old school of just seeing it on paper,
right?
Do any of your principles adapt around that? For instance, given your example at the start around like Power BI dashboards and whatnot, and people can now drill down into data with basic examples on top. Do those principles
none of the principles I've presented are negated by modern tooling. I deliberately stayed away from tooling. The things that are changed, the drill down stuff, the interactive stuff, and the animated stuff are improvements that you can't get on paper. It's hard to drill down into that. So, but even then, when you drill down, you'll see another graphic. And that graphic should apply the same principles of visualization. You should still be thinking about the data, what is the data ink, and how you can maximize that with reason. You should be thinking about representing it with integrity. You should be removing redundancies and as much metadata, meaningless metadata or junk as you can. There's nothing that modern tooling undoes of what it does. It just adds some tooling. I think one really big one is that I showed the multiple changes where you could change over time. That you could do with animation now, which you couldn't do before. Even with computers, that's a relatively new, like last 15 years that tools were able to animate.
All right, thank you.
All right, thank you. 1 minute if anybody's got a question. Yes, sir, right here.
Just funny if I was going to make a similar point. That I don't think of these things in themselves, but I think you can push further into your data ink ratio if you're able to interact with the graph.
Fair point.
You can get rid of grid lines and simplify y-axes and things if, for example, you can put a cursor on instead. So you don't have to see everything as being, I could put this in a book or I could put it on a PowerPoint slide, because somebody can interrogate it further if they want.
For the rest of the audience, you made a great point, which is that you can reduce your data ink ratio further because you know that they can drill down into it and they can see that details. Because there's a temptation if you only have one piece of paper, you want to get everything crammed into that one piece of paper because that might be of interest to the users. But if you've got something interactive where they can click on a data point and go further into it, that reduces the need to do that, and therefore would reduce the data ink of each individual graphic. That's a great point. Thank you. I'm going to steal that and put that next time I give this presentation. I am at time, but I'll hang out here in the hallway if anybody has any questions. Thank you so much. Oh, you can clap again. That's cool.